Hello everyone, welcome back to my YouTube channel once again with some new interesting topics. Today we will discuss about the staircase pressurization system, how to calculate staircase pressurization system, air requirement for pressurization system, how much pressure is required, how much the door force is required. So we will just learn how to calculate the staircase pressurization system and how to calculate the requirements for this staircase pressurization system. So first we will learn what is staircase pressurization system. In this practical example, I will calculate the air requirements for this building, which is already done by me. Here you can see this is the staircase. It will go from the top up to the bottom of the building. Let's see the riser diagram. Here you can see this is the 21st floor and this is the basement. So this staircase is connected from the top up to the bottom. We need to pressurize this system like this way. You can see there is a staircase pressurization fan interlocked with the fire alarm control panel, FACP panel, and this is the motorized damper. We'll explain why we use this smoke damper. Uh, so here you can see we have provided grills for air in after every leaving one floor and add another. So this is the way you can put your air grills. You can put after every two floors or every one floor. So it depends upon on you and the site requirement. So let's start uh, regarding the calculation. In this building is divided into two parts. One staircase and the other side, which requirement is 18,000 CFM, and another staircase which is connected from a 21st floor up to the basement. It's 20,000 CFM. So we will start from the top of the building or from the bottom. You can start from anywhere because the staircase is same from the top to the bottom, and one is this and one staircase is here. We will calculate for this staircase requirement. For this staircase you can see there is a one door, and the hall, this corporate hall is open, and maybe in future this will be closed and there may be some doors for evacuation. In case of fire, when a fire happen in this particular area or this area or lobby, so the smoke will start flowing toward this area. So we need to pressurize this staircase to remove the smoke and move out the smoke out of the staircase, so the people can travel outside of the building easily without any smoke. So this is the basic principle of staircase pressurization system. Let's start for calculation. For calculation, we need these parameters like wall, floor, ceiling, and door. These are the like wall, floor, and ceiling are the construction material, and these are the different door frame, type of door frame, and total leakage floor area. So we will need these parameters to calculate the air requirement for staircase pressurization system. Let's start from the beginning. First, we will calculate the leakage area for the walls. What it means, like uh, when a fire happens, the smoke will flow this way, and the staircase the fan pressurize the staircase, and the smoke will go out. So there must be some cracks on inside these walls. There must be a pressure loss to these walls, maybe some holes, some minor cracks, minor leakage. So these are the standards we will use according to the NFPA and ASHRAE. So let's start from the wall. The wall height of the one floor is 12 feet and the length is 17.5 feet, which is this length and this width. This is the 8.5, 17.5, and height is 12.5. So you can see here one side is 17.5 and one is 8.5 and the height is 12. So put it here, the length and width of these wall, and the area will be calculated automatically. How I calculate the area, you can see here, this is basically the parameter. Uh, the wall are on the 1, 2, 3, 4 walls. So I just took this width and this length and add these two and multiply by 2, so I get the total floor area, the total parameter of this staircase, which is 624. And where I get it, these numbers 0.11 times to power minus 3 or 0.0010011, how I calculate this, or from where I did get these numbers. Let's go to the ASHRAE. Uh, sorry, NFPA. Here you can see the stairwell wall. This is the table A 4.4.3 NFPA 92. You can just read yourself by yourself in the NFPA this standard 92 code. So stairwell walls include construction cracks average, which is 0.11 multiplied by 10 raised to the power minus 3. So I take this and put it here. Same for the floor. Here you can see uh, exterior building walls and floors. So for construction gaps through floors, which is 0.5 to 10 raised to the power minus 4. This number for floor, same length and width of floor, and put the average leakage. So the total leakage will be calculated here. How? It multiply the average leakage ratio with area. So you will get the total leakage area of the floor and total leakage area of the wall. So these two parameters are calculated. These are simple: length and width of floor, length and width of wall. So this will be calculated automatically. Same for the ceiling. The ceiling is same as the floor. So the leakage area is 0.01547. And now we will calculate the leakage through door. There may be some gaps beneath the door, so when the staircase is pressurized, the pressure will be lost to this area, to these cracks. So we will calculate the total door leakage area, which is 0.12. How I calculate this? You need to add the height of the door frame, width of the door, and the area will be calculated automatically, which is the round about 21 square feet. Sorry, 20 square feet. These are all in square feet, feet and square feet. And 0.006 is the average leakage ratio for the door frame. So the total area through the door, which door? I am talking about this door. How much air will be lost through this door? So this is the leakage area of the door frame. So when you calculate all of them, add these total area, you will get the total leakage area through floors, doors, and these construction material. And second thing is how much pressure difference is required, like how much pressure difference is required across this and this adjacent areas, inside and outside of the emergency staircase. What will be the pressure difference? How much pressure you need to add in the emergency staircase to make the pressure differential of 0.37. This is the maximum 0.37 inch water gauge or 90 pascal of pressure you can maintain. Above this is not recommended. So we will go for this. Here you can see the minimum pressure difference across the staircase and the adjacent accommodation space according to NFP 92A table 5.2.1.1, which is 0.8. This is the minimum, and 0.37 is the maximum according to the IBC 2006 section 909.7.2. So I took the maximum and added here. Now this is the equation to calculate the airflow through construction gaps. What are the construction gaps? Construction gaps are wall, floor, and ceiling. These are the construction elements. So we need to calculate the airflow through these cracks. Like this is the total leakage area of the construction elements, and this is the CFM airflow will flow through these leakage at the pressure of 0.37. So I just put these value, and these everything will be calculated automatically. I will explain how I calculate it. This is the equation of 2610 into 0.10 leakage area into feet square, and uh, pressure power pressure under root or pressure power 0.7. This is the 0.37 power 0.5 or under root of 0.37, and multiply all of these, you will get the total CFM, total airflow through these construction gaps. This is the equation. You can also check here. 2610 multiplied by total leakage area through to construction elements, not the door. The door is separate. And 2610 uh, uh, into leakage area multiplied by into pressure difference under root. So you can check yourself according to these equations, and this is the when doors are open. We will discuss it later. So we calculate the airflow to construction gaps, and now we will calculate the air flow requirement through the door gaps. When there is a door gaps, we calculated the door gap, which is 0.12, and we will calculate the airflow to this leakage, so which is 63 CFM. Now we will calculate the total flow rate per floor. So add these two. This is the 221 CFM, which is the airflow through the cracks through the leakage area. This is the CFM through the leakage area of door and construction elements like wall, ceiling. This is the 221 per floor. This is only for this floor, but we don't need for one floor. We pressurize the whole stair well, which is from, like you can see, from the top to the bottom. We need to pressurize whole this these floors, which is from basement number 3 to up to 21. So what are the number of floors? In this case, these are 25, because these are three basements, and then ground floor and first, second, these are completely 25 floors. So the total CFM through all floors through leakage area of a construction element and door is 5518 CFM. This is done, and now we will go for second step, which is the like when the fire happened, the doors are closed, the stair is pressurized, we need this CFM. And now in second case, when the door is open and the air will flow through this door, there will be a door opening which is 7 by 3 feet. When the door is 7 by 3 feet, single leaf or double leaf. In this case, we have a single leaf door. Sorry, let me go again here. Here you can see it's a single leaf door, and in single leaf door size is 7 feet height and 3 feet width. The area is 21 square feet, and number of door opened during evacuation. When the fire happened, which doors will be open? In this you can see this door will be open, the people will flow this way, people will go this way, and there is another door in other floors. When, like, let me show you to clarify your concept. Here you can see when the people sorry, here. Here you can see when the fire happened, the people will will go from this area to this area. So this door and this door will be open. So we usually consider three doors, but in this practical example, we will check how much doors are open during evacuation. So I consider two doors. One is double leaf and one is single leaf. Here you can see this is a double leaf door and this is a single leaf door. These two doors will be open when the fire happened and the people will evacuate through this way. So when you add these parameters, the Q3, which is the airflow when the door is open, here you can see airflow velocity of not greater than 200 fpm. We will consider 200 fpm maximum velocity when the door is open and the air is flow to this door. To doors when three doors are open. IBC consider three doors during evacuation, but it depends on your requirement, or you can consider three doors. There are three doors are open, but it's a practical example. I know how much doors I have which will be open during evacuation. So this is the equation Q3 Vmax. Vmax is the velocity maximum airflow velocity when the door is open, and the door will flow through the opening of the door. Like the how when the door is open, the air is flow through 7 by 3 feet, which is 21 square feet, and 42 square feet. The pressure will be lost, but we need to maintain the exact 0.3790 pascal pressure difference. So when we need to maintain this pressure in case there is a when the door is closed and the door is open, we need same pressure across the adjacent area. So we need to add this CFM also to the total flow for staircase to calculate the total CFM to maintain the 90 pascal pressure inside adjacent area in case of door is open, in case of door is closed. So when uh, you people will think when the where will be the 18,000 CFM will go when the door is closed. There must be a relief damper. I will explain it later. So in this case, I consider two doors. I calculate the area here and I calculate the Q3, which is 12,600 CFM. How I calculated area into 200 FPM. This is the 200 FPM, the maximum velocity according to IBC when the door is open. So this is the 12,600. I add these two values. This is the 18,118, the total CFM that I will need when the door is open. And when the door is closed, this much CFM I require. But I will consider the staircase pressurization fan according to this CFM, not this one. Why, I will explain it later on the bottom of this section. Here we will add 10% factor of safety, which is 19,930. We will consider 20,000 CFM fan to maintain 90 pascal across this adjacent area. When the door is closed and when the door is open, there must be a 0.37 or 90 pascal pressure at, regarding this adjacent area, and this fan will do its work. Sorry, this is the uh, these are the sorry, this is the 20,000 CFM, and this is the 18,000 CFM. These areas are same, just the difference of floor. It depends upon on your floors. If they are 25, you will add 25. If you are 24, there are 10 floors. Depends upon on your requirement. So let's uh, go for the air relief requirement. I said that when the door is open, the air, let me explain it in a better way. We will go to this way. Here you can see there is a fan, the duct going down up to the bottom floor. It's sorry for this one. This is the 20. This one, sorry. This is the 20,000 CFM. So the duct will flow up to the bottom, connected with the different grains. So this will pressurize the system. But here you can see I added the pressure differential transmitter. The pressure differential transmitter basically connected with the this fire alarm control panel and also the fan. It will show the uh, pressure like when the door are closed and the fan is flowing providing a 20,000 CFM. It will not create a 90 pascal pressure. It will create more than 90 pascal pressure. It may be a 120, 130 or 200 pascal, but we don't need 200 pascal. We need a 90 pascal. This 20,000 CFM are required when our doors are open during evacuation, not when the doors are closed. When the doors are closed, how much air we required? 5518, only this one. How fan will know how much air I need to provide? This pressure transmit differential transmitter, that is PDT, it will provide a signal to the fan that the pressure is exceeding above 90 pascal. So it will slow down the fan connected with a VFD, variable frequency drive. Variable frequency drive slow down this fan and the 90 pascal pressure differential is achieved. When the people are evacuating, open the door. When some people open the door, the pressure will be lost and the pressure differential transmitter give a signal to the fan to increase the speed, to provide a signal to the VFD to speed up the fan and provide a 20,000 CFM. It will flow, it will blow at the maximum speed to maintain a 90 pascal when the door is open. So this is the basic criteria. And in case of failure, when the PDT failed, there must be at the top of the building, there must be a pressure relief damper. When the pressure exceeds 90 pascal and the pressure transmitter is not working and the fan is blowing at 20,000 CFM, the pressure relief damper will open and it will relieve 14,412 CFM to maintain again this pressure when the door is closed in case of failure of PDT. So this is the total calculation and total criteria of this building. You can get the all standards here, and you can calculate the pressure across the floor, which is maximum 30 pounds. Total door opening force is 30 pounds. That you cannot maintain more than 90 pascal. So when the pressure is above 90 pascal, the door pressure, the door opening force is exceeding 30 pound. The people cannot open the door because of the pressure. So the people cannot evacuate this building. So you need to maintain 30 below 30 pound force and 0.37 of the pressure differential, maximum pressure differential across the doors, which I already put it here 0.37. You can read it yourself. If you have any question, you can ask me in the comments, or any type of confusion, you can ask me anytime. Thank you very much for watching my video. Keep sharing my video and keep me updated if there are any I'm open to any question and open to any comments. If there are some mistakes, if there are some suggestions, you can comment, please. Thank you.